Okay, so good morning, everybody. I'm Antoine Vastel from the University of Lille and INRIA, and today I'm going to present joint work with Pierre Laperdrie, Walter Rudametkin, and Romain Rouvois about our approach, FP Stalker, that evaluates the effectiveness of browser fingerprinting for tracking. So let me briefly explain what browser fingerprinting is. So traditionally, the technique to track people on the internet is to use cookie. So when a user arrives on a website, the website generates a unique user identifier and assign it in a cookie so that when the user comes back, it can be tracked and an advertiser can, for example, build a browsing profile of this user to propose targeted advertising. The goal of browser fingerprinting is to do this without storing anything in the browser or in the user's device. So that means that even if the user deletes its cookies or goes in private mode, browser fingerprinting can still track the browser. To do this, it relies on the fact that different users may have different device configuration. And if this device configuration is quite unique and stable over time, then this configuration could be used as an identifier to keep track of the user. So what we call a browser fingerprint is simply the combination of attributes that are either sent by the browser, such as some HTTP headers, for example, the encoding headers, the languages, or the user agent, or other attributes that can be collected in the browser using JavaScript, such as the canvas, the platform, or the screen resolution. State of the art has shown that fingerprint uniqueness is around 80–90% depending on the dataset. But uniqueness is not enough for tracking, because if you keep being unique, but every time you're unique in a different way, it may not be possible to track you. So the goal of this paper was to evaluate the fingerprint stability first, and in a second time to evaluate the effectiveness of browser fingerprint tracking. So this research could not have been possible without Am I Unique? So Am I Unique is a website that enables you to see your fingerprint and see how unique you are. We also have two browser extensions, one for Chrome and one for Firefox. And so we use this data set for this paper, so the browser extension data set collected over a 2 years period. And it contains, once it has been filtered, around 98,000 fingerprints from 1,900 browsers. So we removed users with less than 7 fingerprints for this study, and also users that have a countermeasure installed. So our first finding is about fingerprint stability. So we show that stability varies depending on the attributes and on the user. So in the table, we see for different attributes such as the screen resolution, the time, the attribute remains constant. We see that for the screen resolution, half of the user, so the 15th percentile, have a fingerprint that never changes, have a screen resolution that never changes. And for other users, so if we look at the 19th percentile, for 10% of the users that change more often, the screen resolution evolves every 3 days on average. So this difference can be explained by the fact that some users may have an external monitor. And for example, when you go to work, you plug your laptop to an external monitor, and when you come home, you unplug it. And so for some user, it changes regularly. But for other users without an external monitor, it may remain constant for a long period of time. Other attributes, such as the user agent, evolve more uniformly across all users because it contains the browser version, and since browser may get updated regularly, then it evolves for all users. And finally, there are other attributes such as the accept header or the cookies, so whether or not user accept cookies, that are much more stable. For example, if we look at the cookies, for 95% of the browser in the dataset, the value never changes. So now the goal is to evaluate fingerprint tracking. So let me briefly define what we mean by tracking. So in our case, tracking is the process of linking different fingerprints from a given browser. So when a website collects fingerprints, you want to link it with fingerprint in the database and assign the right identifier. So we have two options. The first one is during the linking process, the algorithm finds an identical or a similar fingerprint and then it can link the new fingerprint to an existing browser identifier. Or the algorithm find no or too many similar fingerprints, and in this case, it may decide to assign a new browser identifier. So we proposed a rule-based algorithm whose goal is to, given two fingerprints, decide if they may originate from the same browser. So we have a set of strict rules because we do not expect the operating system, the platform, and the browser to be different between two fingerprints from the same browser. We also do not expect the browser to be downgraded. Then we have rules that have been extracted from the statistical analysis conducted. So we saw that some attributes such as the local storage or the canvas are quite stable over time. So we consider that for two fingerprints to originate from the same browser, they must be identical. Then we have other attributes that may evolve sometimes, such as the user agent or the headers. So these attributes can be different between the two fingerprints, but with a similarity greater than 75%. So this threshold has been chosen because of the only state-of-the-art paper realized by in the panoptic paper that use fingerprinting for tracking. And finally, other attributes such as the resolution of the time zone can be different, and no more than two attributes can be different between the two fingerprints. The problem with this approach is that even though it performs quite well for tracking user, as we will see in the results in the evaluation part, but it's difficult to create complex rules manually. We can do better. So we propose another approach that is an hybrid approach that relies on strict rules first to filter the potential number of fingerprint candidates. And in a second time, we apply machine learning to obtain a better accuracy. So the goal of our machine learning model is given two fingerprints to compute a probability that these two fingerprints originate from the same browser. We choose a random forest. So a random forest is simply an ensemble of a decision tree, and each tree makes a vote, and in the end, the result is the majority of the vote between the different trees. We choose a random forest rather than models such as a neural network because it provides a good trade-off between precision and interpretability. So in this presentation, I don't interpret the different attributes and features of the model, but you can find more results in the paper. But machine learning model performs on a vector of numbers, and fingerprints are mostly set of a combination of string attributes. So the way we vectorize our fingerprints is the following. So if we have a new fingerprint FP new and a fingerprint in the database, when we compare the two fingerprints, we do mostly pairwise comparison, and we extract a string similarity for attributes such as the encoding of the languages. For other attributes such as the canvas, we extract only a binary value, so 0 if the two attributes are different, or 1 if it's the same. And we also added new features such as the number of changes, so the number of differences between the two fingerprints. Then we can train our random forest model. So we train it on 40% of the dataset ordered chronologically. And we feed pairs of fingerprints to the model. So we show pair of fingerprints that comes from the same browser and pair of fingerprints that come from different browsers. And we apply undersampling to reduce overfitting. That means that if you take randomly two fingerprints in the dataset, most of them will come from different browsers. So we readjust the proportion of fingerprints that come from the same browser in the training set. Finally, we can go to the evaluation. So to evaluate the effectiveness of browser fingerprint tracking, we conduct the evaluation on the test set of around 60,000 fingerprints from 1,400 browsers. So to explain the protocol and the different metrics and why we choose these metrics, I will go through a small example. So if we consider that we have three browsers, A, B, and C, with different fingerprints, the first step is to generate a fingerprint sequence. So we order fingerprint in the way that they would have been collected, but we simulate the effect of the fingerprinting frequency because we want to test whether or not collecting a fingerprint every day or every 2 days or every 3 weeks has an impact on the possibility to track a browser. The idea is that if you collect a fingerprint every day, there will be less changes probably than if you collect it every 3 weeks. And finally, we can apply the linking algorithm. And what we obtain is different tracking chains. So a chain is simply a set of attributes that have been linked by the tracking algorithm together. That means that the algorithm considers that they belong probably to the same browser. What we see in this example is that chain 1 contains both fingerprints from browser A, but there is also a mistake because the linking algorithm added a fingerprint from browser B in yellow. In the case of an advertiser that will try to use fingerprinting for collecting data, this means that it will mix profile of two different browsers or users, and the data would be sort of polluted. If we look at chain 3 and 4, we see that so the algorithm splits data from fingerprint from browser C in two different tracking chains, which means that the advertiser probably will think that it belongs to two different users and will lose some value. So the first metric we use to evaluate the effectiveness of browser fingerprinting for tracking is average maximum tracking duration. So the tracking duration is the period of time a linking algorithm correctly matches the fingerprint of a given browser instance in a single tracking chain. So for each user, we take the maximum time it has been tracked, and we average it over all of the browser. So in green, the highest line, it's the hybrid version. So the graph represents the metric for different collect frequency, and we see that the hybrid version, on average, is capable of tracking a browser around 75 days on average. But we also see that the performance slightly decreases as the collect frequency increases. Just below in orange, we have the rule-based version of our approach. So we see that this version is more impacted by the collect frequency, because when the collect frequency increases to 20 days, it tracks only browser for 60 days. And we also compared with the panoptic algorithm proposed in 2010 by Eckersley, which is the only state-of-the-art algorithm that rely on a fingerprint for tracking browser. The second metric is the ownership. So the ownership of a chain can be seen as the purity of a chain, or it reflects the pollution or the quality of the data. So once again, if we look at chain 1, it contains fingerprint from browser A and one fingerprint from browser B. So we can consider that chain 1 is owned at 80% by browser A and polluted at 20% by browser B. So this metric reflects how good is the data collected. If we look at the average ownership, what we see is that once again, so the higher is better, the closer to 1. The hybrid version is around 99% of average ownership, and the performance also slightly decreases as the collect frequency increases. The rule-based version is really close to the hybrid version, with performance around 98%. And once again, panoptic version is performs a little worse. It is more impacted by the collect frequency. So when the collect frequency is around 1 day, it has an ownership of around 96%, and the ownership goes down to 93%. Now, if we look in detail at the hybrid version, because it is a better algorithm for tracking, and if we set a collect frequency of 7 days, so we choose this number because it's a week, so it's the case where someone goes on a website every week and gets its fingerprint collected. So the graph represents the percentage of browser that can be tracked a certain amount of time, and in gray, so the highest line represents the perfect tracking time. So that's what we could have achieved if we had a perfect tracking algorithm. And just below in black, we see the same graph with our algorithm, the hybrid version. And if we look at the intersection with the green line, we see that 26% of the browser could be tracked more than 100 days. But on the opposite, there is around 20% of the browser that cannot be tracked more than 25 days on average. Which means that on one side, we have users that are really unique, which have a unique fingerprint, and that can be tracked easily for a long period of time. But on the opposite, we have also fingerprints, a browser with more common fingerprints, and which are much more difficult to track. So I will conclude this talk. So we saw that fingerprint tracking requires both uniqueness and stability. Our first finding was that stability depends on the attributes We thought that, for example, the screen resolution may evolve more frequently than attributes such as the local storage or the accept headers. But it also depends on the user, on the browser, or on the context. Some users may have an external monitor and may change their screen resolution often. Others may travel a lot and may change their time zone frequently. We propose two approaches, one based on rule. So I didn't show it in this presentation, but in the paper we ran a benchmark on a generated dataset of 2 million fingerprints, and the rule-based version takes around 100 milliseconds to match a fingerprint, and that's around 5 times faster than the hybrid version. But on the opposite side, the hybrid version is capable of tracking browser around 10 days longer on average. And so in our dataset, we could track 26% of the browser more than 100 days. But on the contrary, there are also browsers that are much more difficult to track because they have more common fingerprints. Thanks for your attention. If you have any questions, I'd be happy to answer them.
Hi, this is Ben Stock from CISPA. Very interesting work. First, one technical question. Local storage, how did you measure kind of similarity? You stored a value and checked if it was still there, or?
No, in fact, local storage and cookies is, so the attributes reflect whether or not the user accepts to store anything in its browser. But we do not store anything, we just check if we can do it. Okay. So we test only the binary if the value is the same for the two fingerprints.
Okay. And I was wondering, I mean, so the data that you're collecting and also that Eckersley was collecting is always people that go to that website. So is there kind of a sampling bias in those people that are there?
Exactly.
Because I'm just thinking that like a regular user would not have any custom fonts, any custom extensions, would just have Windows and, I don't know, Internet Explorer running, right?
Yeah, so maybe at 3W, there was another paper by one of the co-authors, and they collected data on a popular French website. And so they had a uniqueness rate of around 40%. So this shows that our data set is biased, of course. But I think it reflects something is that people that care about privacy and that have probably less common fingerprints can be tracked. But probably the proportion of users that are vulnerable to tracking using fingerprinting are less high than what we may show in this data set.
All right, thank you.
Any other questions? I have a quick one. Do you know if there's any data on how often people clear their cookies? Because that seems to be relevant to how long they can be tracked as well.
Yeah, so there are different studies, but I don't really remember the numbers. But I think it could be used like even without totally deleting the cookies. Some people may want to go in private mode because sometimes you may not want the website to know that you visited it multiple times to check for a flight ticket, for example, and people may not delete their cookies, but simply go in private mode. And this could be used to see that it's the same person.
Right. All right, let's thank Antoine.